Welcome back to Physics 151 Online. In the real world, we're often interested in studying objects that are not really a collection of discrete particles, but are continuous in nature. And so, how do we find the center of mass of a continuous solid object? Experimentally, we could do that by trying to balance the object on a single point near the Earth's surface under the influence of gravity. And if we can find that balance point, that's a very good approximation to the true center of mass. If we have an object that's got an irregular shape, then sometimes we can break that object down into smaller pieces, each of which has a shape where we can find the center of mass of that piece. And then we can weight each of the positions of those center of masses appropriately by the mass, and then find the overall center of mass of the entire object. But sometimes the object is non-uniform, or its shape won't allow us to use that simple strategy that I just mentioned. In these cases, we can use really nice applications of calculus to add up the contributions of all the different pieces to the center of mass. So schematically, let's imagine that we have an object like this one here, where there's a certain total mass, and we will break this object down into smaller mass pieces, each of which we will call delta m. And so the idea is going to be we will find an expression for the center of mass, assuming that the object is made up of lots of these little pieces, and then we'll take the limit as the mass of those pieces gets smaller and smaller. So here is the definition of the center of mass position. It's defined as the summation of the mass times the position of that object with respect to the origin divided by the total mass. But if we take the limit where that size of the mass gets smaller and smaller, then we can replace this summation with an integral. And so the integral of the position of a piece of the object times the differential amount of mass it contributes, integrated over the entire object, divided by the total mass, gives us the position of the center of mass. So the integral, of course, in order to take into account all the contributions, has to extend over the entire object. And dm simply represents symbolically what the amount of mass is in a differential sense that is associated with each of those pieces. Now this by itself is pretty abstract. How do we actually apply this in a real situation? So there are some steps, and you'll get a chance to practice with these on the homework. You first, as I showed schematically, divide the object up into very tiny mass elements, and each of those mass elements we assign an infinitesimal mass dm to. So draw that typical mass element, and you have to draw it and exaggerate its size a little bit so that you can see the detail in your sketch, but you label it with its correct size, which usually has some kind of length element like dx or dy on it, and then its position related to where the origin is. Then we use the other information about the object that we're studying to write down an expression for dm in terms of those other quantities, which might include the size of the object and its total mass. Finally, we actually go ahead and solve for the center of mass position. We set up the integral that's in the numerator, the integral r dm. We choose the correct limits of integration to make sure that we're adding up the contributions of the entire object, and then the denominator term is the total mass. And so sometimes we may have to integrate this dm quantity in order to obtain the total mass of the object. And finally, we take the ratio of those two integrals in order to solve for the center of mass position. Now, in many cases, we'll have problems where we will find it easier to solve for the components of the center of mass position, the x, the y, and the z coordinates of the center of mass. And so in my example, you'll see this quite clearly. Here's an example. I won't work out the solution entirely, but I'll set it up and show how one approaches a problem like this. Imagine a one-dimensional rod, but is non-uniform in length, in its mass. So here is a simple model that shows how the mass per unit length of such a rod might increase as we go along the x-axis. So at x equals 0, then the mass per unit length which the symbol lambda represents, would simply be given by a constant lambda 0. So over here at the left-hand side, there would be a certain mass per unit length, but as x increases, the object gets more and more mass per unit length. It gets thicker. And this, although the shape doesn't reflect it, this might be a model for something like a baseball bat, where it's tapered at the left-hand end near the handle, and it gets thicker and thicker as we move out toward the end of the bat, and so it has more mass per unit length on the right-hand side than it does on the left-hand side. So for such an object that has a mass per unit length given by this equation, how do we actually find the position of the center of mass? By symmetry, we know that the position of the center of mass will be on the x-axis. The y-coordinate and the z-coordinate will be 0. So let's go through the steps that I just outlined to set up the solution to this non-uniform rod problem. First of all, we carve up the rod into mass elements, label them as being dm, and then what would be important about this mass element is it would be at a position x with respect to the origin, and it would have a thickness dx, a size dx. We have to write these things in order to set the integral up correctly. So next, we'll write an expression for the differential amount of mass, the infinitesimal amount of mass associated with that mass element, dm. How do we do that? Well, dm is going to be the mass per unit length of the entire rod multiplied by the length of this element, right? And so the length of the element is dx. What's the mass per unit length? Well, that's simply lambda of x, which is what we were given, right? We're given an expression for that. So look at this carefully and make sure that you understand it. The amount of mass associated with that piece would be the mass per unit length at that point multiplied by the length dx. And so that would simply be given by lambda of x times dx. So that's an important relationship, and it allows us now to set up the integral that will give us the x-coordinate of the center of mass. So going back to the definition, the x-coordinate of the center of mass is the integral of, instead of r dm, I'm just going to write x dm because it's only the x-coordinate of the mass element that we care about. Integral of x dm divided by the total mass, and we're not given a symbol for this, we're not told what the total mass is, so we actually have to evaluate that by adding up the mass of all the pieces. And so, using the expression for dm that we just determined, we plug that into these two integrals. So in the numerator we get the integral of x lambda of x dx, where we would now take that expression for lambda of x and plug it in, and the denominator is just the integral of lambda of x dx. So we would actually work out these two integrals, divide them out, and that should give us the x position of the center of mass, and I'm suspecting that our answer will contain in it the length L as well as this constant lambda 0. So that's how you set up a calculation for the center of mass position of a non-uniform object. Now the last new topic that I'd like to introduce today is impulse. And impulse is just a quantity that's defined because sometimes we would like to be able to answer a question in a quantitative way. A question like, how hard did the batter hit the ball when he swung and sent it flying into the outfield? And so to answer questions like that, another similar question might be, how much impact did the collision of the car with the wall have? What did that do to the car? And so the impulse is defined, and the symbol used for that is j, and it's a vector because it's defined as the final momentum of the system minus the initial momentum of the system. So it's just delta p. Remember, as we're going through this part of the course, that momentum is a vector. It's got not only magnitude but direction, and as a result, impulse has a direction associated with it as well. So in order to flesh this out in a little more detail, to relate the change in the momentum to some other quantities, we can rewrite Newton's second law in a very useful form. So remember, Newton's second law said the net force, the sum of all the forces acting on an object, is its mass times its acceleration. And if we substitute for acceleration as the derivative of velocity with respect to position, and then realize that, that mass that's multiplying the velocity derivative can actually be brought inside the parentheses here so that we're taking the derivative with respect to time of the product of mass and velocity, then mass times velocity, we've already defined that as momentum. And so we see that a more general version of Newton's second law can be written this way, as the net force acting on an object is equal to the time rate of change of momentum. So what this allows us to do is now write an expression for the small change in momentum associated with a net force acting on an object over a small amount of time. So I'm solving this equation for dp to get an expression for this tiny change in momentum when a net force acts on an object over an infinitesimal amount of time. And of course the reason I do this is because I would like to now sum up the influence of this force over a finite amount of time in order to get the total change in momentum. So integrating this quantity from an initial time to a final time gives me p final minus p initial, which is just delta p, as the integral of the net force dt from t initial to t final. So this result is often written in terms of J, and people call it the impulse momentum theorem. So we defined J to be the change in momentum, and now we see how that is related to the influence of a net force acting on an object over a certain amount of time. And I'd like you to compare this to something that we've seen already, because you'll see similarities in it, and that is the work-energy theorem. Remember that the work-energy theorem, once we defined what we meant by kinetic energy, the work-energy theorem said that the net work acting on an object is equal to its change in kinetic energy, and that's equal to the integral of the net force dotted into the displacement as the object is moving from an initial to a final position. And so you'll notice that both the impulse momentum theorem and the work energy theorem relate changes in an object's motion. In the top equation it's the change in momentum, in the bottom equation it's the change in kinetic energy, which means the change in speed, and they're related to the influence of the net force. In the top equation, that net force, we have information about how it acts on an object over a certain time, while in the bottom equation we have information on a net force acting on an object as it moves between two positions. So which one we use for a given problem just depends on the available information. So one more thing with the impulse momentum theorem, sometimes that net force changes with time in a really complicated way, and we can't necessarily predict what that's going to be in advance. And so sometimes we'd like to relate the change in the momentum not to the specific details of a changing force, but maybe just the average force that acts between these two times. And so we can take that relationship for delta p as the integral of f net dt and just say we'll set that equal to an average force acting on the object between t initial and t final. And so that comes out to be just the average force vector times delta t. And this expression is helpful when we're looking at collisions, maybe between a bat and a ball, where we know the initial momentum of the ball as it comes toward the bat, and we know the final momentum of the ball as it leaves the bat. And if we know the time during which the bat and the ball were in contact, we can use that information to calculate the average force that the bat exerted on the ball. And you can see your homework assignment for an example problem just like that. I hope this has been helpful, and I will see you in class.